This is the AI of Things panel. And we've got basically half of MIT here who are working on this, as well as a few of our favorite experts. This is important. It's moving quickly. And we're going to get to the bottom of it with a esteemed panel. Maybe I will let you, Annika, you can start. Maybe instead of me just giving the Cliff Note version, you can give a 30-second intro of yourself and what you bring, and will come all the way from you to me, of what kind of your slice of this world of physical AI.
Hi, everybody. My name's Annika. I'm a PhD candidate, and I work more on the side of robotics that has to do with vision and perception. And my kind of slice of this whole body of research is working on methods where robots can collaborate. They can share different representations of the world with one another in intelligent and efficient ways.
Yeah, hi everyone, I'm Caleb. I'm an undergrad here.
What's a Z fellow?
It's the fellow that comes after Y.
Ask a stupid question.
But I'm working with accelerating AI compute and AI chips.
Yeah, fantastic. Hi, I'm Thomas Baker. I specialize mostly in deep tech and then building in robotics and in robotics in extreme environments. So I spend a lot of time in the advanced concepts team with Blue Origin, in rocket design and propulsion, and then into robotics and AI, and getting AI into space and how we would build and how it can work in situ.
Daniela, we know, right? Yes. But give us a CSAIL, the CSAIL take.
Well,
what you guys are working on.
My take this time, and not the CSAIL take. So I'm Daniela Rus. I love robots. I've been working for a couple of decades on robots, and robots in water, robots in the air, robots on the ground. And to me, what's really extraordinary at this point in time is that we have seen so much progress with AI in the digital world, but our robots remain primarily pre-programmed. And so what I'm interested in right now is to bridge between the extraordinary learning and reasoning capabilities that we see in the digital world to the physical world.
Sure.
Hi, I'm John Leonard. I'm also really proud to be part of CSAIL with Daniela. I'm also a professor in mechanical engineering, and where I'm associate department head for education. And my research is about robot navigation, how robots can explore the world and build maps and develop internal representations to try to then interact with the environment for underwater, for air vehicles, ground vehicles, sea surface vehicles. And most recently, we're seeing kind of breakthroughs with taking vision language models and applying that to robot navigation and mapping so that robots can sort of develop a knowledge of what is where in the world. I think of it as Google for the physical world. And so it's there's still tremendous challenges, but the progress recently has been kind of amazing.
Well, actually, maybe we'll start with you then, because I saw a lot of nodding out there. Yeah, obviously, you're in an area that a lot of people see. You're one of the, kind of the, how self-driving cars are the great, again, that's what a lot of the layperson thinks in terms of how AI is, how they're understanding AI. What have you learned about intelligence based on what all these years of research in navigation?
So there's something called Marvik's paradox. Hans Marvik was an early roboticist who tried to create a robot in the 1970s to navigate around like the Google car, just in a Stanford parking lot. And it turns out that it's frustratingly difficult to develop a robot with what I would call spatial AI, spatial understanding. And so if a lot of our AI approaches are based on human annotated data sets where humans might, Facebook, Meta has a data set, a technique trained on 1 billion images. That's not how children learn. I think that navigation and exploring the world lends itself to robots that can learn from their own experience from much smaller numbers of samples of data, exploiting the kind of spatial temporal context of the data that they acquire. So that's my dream, as a self-learning robot.
Self-learning robot. And that's one definition of intelligence. Daniela, how are you guys are right in the middle of this thing, maybe the same kind of question, which is that it's like kind of the Terminator question, which is once AI is physical, it's even more important that that safety is factored in there. What are you guys doing in terms of, and what are you kind of working on in that area?
Well, okay, so today's AI doesn't quite fit with robots for a variety of reasons. First of all, the models we have today are too big to fit on the body of the machine. And that's a problem, because if you're in a self-driving car that's driving at 60 miles an hour, and you have to place a cloud call and then wait for a few seconds until the cloud tells you what to do, you might as well stop because the answers will be coming too late. And so for robots, we need small AI that fits on the body of the machine. Also, today's AI makes mistakes. And for safety critical systems like the ones we have with robots, we cannot have AI that makes mistakes. Additionally, the transformers, which are the most prevalent models today, do not do spatial-temporal correlations. But robots move in the physical world where spatial-temporal correlations are important. Additionally, transformers are statistical methods. There is no physics, there's no common sense that is embedded in what you get from transformers. So all of this points to the need to have a different kind of AI that is compact, that doesn't make mistakes, that understands the laws of nature and physics, and that could deliver safety-critical applications. And so in my research group, we're exploring a number of alternative architectures and ideas for making AI solutions. The first one I've talked about in this forum a number of times. The first one is called liquid networks, and liquid networks are inspired by the neural structure of small species like worms. But most recently, we have developed another method which we call linear oscillatory networks, and these ones are inspired by the oscillations in the natural brains. And so these solutions belong to a class of AI algorithms called state space models. And these are physics-based solutions. In fact, the computation is modeled by differential equations, first-order differential equations for liquid networks, second-order differential equations for linear oscillatory networks. And we see great benefits from the point of view of causality, of compactness, of being able to explain how these systems make decisions, and from the point of view of being able to fit them on the bodies of robots.
Danielle, that's a good segue, because you talk about the need to have no mistakes, and Thomas, you were dealing with AI in space. By definition, you cannot make a mistake there. There is no escape. We have to keep Katy Perry safe. It's very important.
She's a national treasure. Right.
She's back. It's very happy. What did you learn working in that environment that we can apply here on terra firma?
I mean, the thing that we wanted to consider is that how, we wanted a system that was able to build effectively a coherence model of its operation. Luckily in space, if you're sent around the Earth 17 times in a day, it's a lot easier to predict. But something that's able to ingest and understand stochastic outliers, right, and then react to them is a much, much harder challenge, especially when we talk what's called in situ resource utilization, right? If I send a robot to a planet and I say, hey, build a house, does it understand what it needs? Does it understand the materials that are around it? Does it understand how to construct everything necessary to then build what's necessary and then handle dust storms and radiation and whatnot? So the problem expands quite a bit, but as far as where we're testing this, right? The ISS is a phenomenal test bed for this, and I'm a huge fan of keeping it going. But we've been able to model this pretty well. As far as the application goes, it's a lot of the work that we're seeing in Daniela's lab that we want to take to other planets and to other places. So I'm really
take it, provided I can come with.
100%.
What, Caleb, I know you've done some work in terms of studying accessibility in this area. What tell us what you're working on there and your thoughts on that?
Yeah, so the chips of today that we see on the bleeding edge are expensive. They have very interconnected supply chains, and they just cost a lot of money. And how do we take the more efficient architectures that we know for computations in AI, matrix multiplication? How do we take that and apply that onto a chip that we can produce at scale from anywhere around the world, and then provide that to people that need to use it. And specifically in AI, how do we do that at a fast enough speed that we can get it in real time? That's been a tremendous impact in all around the world in third world countries. I'm from Ethiopia, and seeing that drones are being able to deliver medicine and be able to fly autonomously is incredible. And seeing that we're able to distribute this around the world is really powerful.
Annika, I opened today with John at 8 a.m. talking about, we talked about the Forbes 30 under 30 a little bit, and how it was digital natives. It was, you see digital natives accelerated the internet. You had iPhone natives and smartphone natives, accelerating app culture. You guys, you and Caleb, are as close as we get to kind of AI natives, certainly robotic natives. Tell us that perspective of having, if not grown up quite, you were younger when you started to touch it. How does that different perspective affect your work?
Younger when I started to do what?
In that I'm just pushing on whether or not you have an advantage because you're younger and because people like you and Caleb actually are as close as we get to AI natives.
Oh, I see what you mean. Yeah, I mean, I'm 26, so I've definitely lived through having a Razor phone, right? Back when I was in middle school, high school. But I would say getting into this point in my life as a PhD candidate, we're starting to see these all the time. I went to undergrad in a time where we didn't have ChatGPT. I learned a lot during that time. But I also learned now how to interpret information faster. And that's something that I want to be able to teach our robots to do as well. I want our robots to be able to parse through kind of this spatial environment and figure out what information is most important to keep, especially when we're looking at these things from a multi-agent setting. We really have to figure out exactly what information to keep in our maps, in our representations, to efficiently share that with one another.
And yeah, I guess as the other young one, I'm 21.
21.
I know.
Nice.
Last month too. So I think the most understated aspect of this is growing up in a world where your agency is actually extremely cheap. And the way you think about the world, I think we try to teach our kids this kind of I can attitude, but I think literally now you can do things physically with manufacturing, you can do things digitally with coding, with designing. I think it's a superpower that we've unlocked to a whole new generation of kids that's actually affordable as well.
Love it. All right, I want to start the conversation with everybody. What's the biggest hurdle we face in the next year or two that we need to overcome, and how are we going to overcome it? Jump ball question.
Can I jump in?
Jump ball, take it.
Yeah, so vision language models have excelled by being able to sort of apply semantics, so language labels to, say, visual objects. But we're missing a sort of language of physical interaction with the world. What does it mean to tie your shoes? We have this intuitive physics with lots of sensing and sort of almost reflexive behaviors built in. And I think that it's not obvious how to take vision language models and apply it to actions. Now, there's been a lot of progress in what's called behavior cloning, where folks will teach a robot how to do a task, like to slip a pancake or wipe a table. And our colleague Russ Tedrake is one of the leaders in that area using diffusion policies. But it's more based on learning from human imitation, but there's not an actual, I believe we need some more of the physics that Daniela mentioned, and we don't have a language for the physics that's accessible to our AI architectures.
Right.
Well, I can build on that and remind us that a robot is the body and the brain. And so in order to have a functional robot, you really need to have a good body and you need to have a good brain. The brain controls the body to deliver its capabilities. The body consists of all the hardware on the body of the robot. And so right now, from the point of view of the hardware, we still don't have all the sensors that are needed in order to get the robots to do more than navigate the world. So if we want the robots to do interaction in the world, yes, we need better sensors. In navigation, it used to be that we were reliant on the sonar. back in the day. That was the only sensor we had.
Yep.
And the sonar is so imprecise, nothing worked. Then someone invented the LiDAR sensor, and all of a sudden the algorithms that didn't used to work with sonar, they all started working. And so we need the same kind of revolution from the point of view of sensing for manipulation, and also from the point of view of fine motors that are needed for dexterity. So that's the... So
it's kind of like, but it's kind of just listening to you guys as the layman up here. It's kind of like instincts where if somebody throws a ball at me, listen, my brain, it is my brain, but it's really kind of my body. It's like...
It's too slow right now, so we need to speed it up. We also need to figure out the energy problem, because our machines use too much energy right now. I can spend an entire day on a bar of chocolate, but my machine will just exhaust its battery within 10-20 minutes. And so we cannot have this kind of lifelong robotics if we do not address some of these hardware issues.
Yes.
And there are more. But there are also issues on the software side, on the brain side. So many people are very excited about the age of humanoids. And we have really exceptional machines that have been introduced. But those machines are really complex mechanisms that are very difficult to control. And so robust control for humanoids will come in time, but not anytime soon. Not today, not tomorrow.
I would think, Thomas, you probably have worked on durability. I mean, space, that's got to be one of the biggest things.
Yeah, I mean, if I'm being completely honest, like I look to like your research, like for the record, PhD and master's, no PhD or master's, mostly bachelor's. So if like I'm truly looking to the research at MIT and looking to some of the technology that's being built here, but integration, and especially in aerospace, integration is always 8 times harder than anybody thinks it is, right? And so integrating sensors, as we do sensor fusion, I lean more towards having multiple of these robots. If I can't have a brain with enough sensors on a singular robot, do I have enough single mode sensors on enough robots around me to establish a vision or so hopefully like close enough omniscience, right? And the same goes for satellite operation.
Tell us a little bit about what the two of you are doing in terms of research and how you're going to help crack what's the big problem both of you see individually, and what you're doing to help solve it.
Yeah, I'm actually going to take the geopolitical and kind of strategic aspect of this, where I think that there needs to be more of a push, I think, from the government to get more involved and expand and create almost like special economic zones or places where people can do...
I'm not sure the folks at Harvard agree that the government should be more involved, but right now...
I think having a more policy perspective, I think, is important so that it's setting up the next 10 years of research. I think there's also an integration problem. I think that a majority of businesses today are not excited to integrate or trying to integrate as much as they could be. And this could be driving massive early gains just in simple performance benefits today that we could be getting, but we're not.
And Annika, you got a multi-robot approach. Tell us about that.
Yeah, so I think when it comes to AI, a lot of us are thinking about it in terms of scale. We're very used to our big data centers. As Daniela said, we have really big models. But if we really want to see this as embodied AI, we want to see this in our physical robots, we can't run these things on board. So instead of thinking about AI in terms of scaling, we have to start thinking about it in terms of structure. We have to think about what information is really vital for the task at hand, and that basically connects with multi-robot applications as well, because when we're thinking about what information each of our robots wants to gather about the environment, they don't need to share all of that with one another. We need to be intelligent with our algorithms for how we decide how to kind of network that information and create a high.
So the robots need to learn to share just like the kids in kindergarten, right?
Absolutely.
Hey, Randa,
Yeah.
can I...
Please, you don't have to ask. That's it. Come on, it's 6 o'clock. We're just jumping in. Go, Daniela.
It's interesting because we all live in a data world. So everything is becoming about data, but robotics is really about the physical world. this idea that we don't need to know anything, we don't need to know physics, we don't need to know math, we just have data that we stick into models and the models tell us what to do, it's just not the path forward for robotics. So we have to be very aware of the pitfalls of strategies like that, and aspire to do more, aspire to find the right solutions that capture the realities of the physical world and the tasks that these machines have to do.
Listen, I've got a couple fun questions, but before I do, what's fun about this event is a lot of people in the audience are, as smart, certainly smarter than me, and it's sometimes as smart as the panelists. What do you got?
I think I have a question about sensor data, integrating sensor data. LiDAR is a very precise way of perception, of perceiving the world using LiDAR, but it's very a-human. Is it challenging to integrate LiDAR data? For example, are there multimodal models that can perceive point cloud data and use it? Or do you have to abstract it so that the model can then work with that data?
So we can collect data, and in general, collecting data is not so difficult. What's more challenging is collecting data that captures the physics of the interaction, because machines, robots, are dynamical systems. In order to get them to operate correctly in the world, we need force and torque information. And this cannot be easily extracted from watching videos or from looking at pictures. So any kind of methodology that collects data for tasks that involve moving or manipulating the environment requires some source for the force and torque information.
John, when you were talking about the limitations in the beginning, when robot collects environment's data, it's not efficient in storing it. In a sense, you used a different word. Is that limitation more in the math algorithm part of it, where it's like the encoder having a compressed representation, like that, or is it more from sensor part that Daniela was saying?
I think it's more, the question is about where does the inefficiency come from in terms of requiring like these huge amounts of labeled data for algorithms to work? And I think it is an algorithmic thing. I think somehow we're not able to learn from very few examples the way that, say, a child. Josh Tenenbaum likes to talk about this, and I think in general, simulation has an important role to play, but a famous roboticist said simulation is doomed to succeed. Like, things will work in your simulator, but not in reality. But I have this notion of robot dreaming, whereby a robot takes a little bit of data from its daily experience, it goes to sleep, recharges its batteries, and overnight it's kind of making sense of the data.
That's an hallucination we could all get behind.
Yeah, and sensor processing is really compression. Intelligence is compressing the immense amounts of data streams coming in to come up with something compact that's kind of reusable the next day. And the robot that gets better and better every day, that's my dream.
It's a good dream, John.
Question right up front here.
So you were talking about sharing data, like you're still working on systems, complex systems, robots sharing data with other robots. I had this image that came up around train the trainer. So will we ever get to that point where the mama bear, papa bear, baby bear kind of image, where the papa bear is being able to be smart enough to train a whole smaller kids, if you will, of robots, that you'll be able to really pass that knowledge down onto you?
Yeah, I definitely think that a lot of our robots are going to be learning from demonstration. There are a lot of really talented teams that are working on actually teaching robots to learn from human demonstration. So our humans are our mama bear and our robots are our baby bears. There's a lot of work to be done in that field, especially on kind of those finer motor tasks. It's really difficult to kind of parse through the physical information of the world and deduce exactly what's happening, going back to what John was saying earlier. But I think that that's something we're going to be seeing a lot more of in the next few years.
If the baby bears are the things that go out and collect the information as well and bring it back, you can refine some of the teaching too.
All right, last question here.
Hi. So yeah, you mentioned how with the advancements in robotics, we'll need a lot more computation. So my question is, like, how do you think that quantum computing can affect the advancement of AI and robotics? And if we do see a breakthrough in quantum computing, how long do we have until a human-like robot is possible?
Well, earlier today on the stage, we talked to Jack Hidari about his company, Sandbox AQ, and he shared with us some examples of quantum sensing. So quantum sensing is more advanced than quantum computing. And I think we can already see advantages from those kinds of technologies. The quantum computers will be able to solve many of the problems that require so much time, so much compute time and energy right now. But that's not around the corner. That's much further.
What's your best guess? Give me a year.
I don't know.
We'll hold you to it.
Let's say 10 years.
10 years, not bad. Anna, what do you think?
10 to 15.
10 to 15. Caleb.
12.
12. It's like Price is Right. $1.
I'd say if we can use the quantum solutions to be able to do better simulation eventually, right? Or get wrapped in the simulation. Hopefully, I'd like that sooner. Whether it's done on the quantum scale,
With a politician, no answer.
All right. I'm done.
I'd say 30. I'm more of a
30. All right. So somewhere between 10 to 30 in our lifetimes. That's a big thought.
Close enough.
I hope my lifetime.
I think you're good. Thank you. Thanks everyone for your time. Great panel. Thanks.
Thank you so much, guys.
So,
Thank you.
Excellent. Thank you, Rando. Thank you, Daniela. Thank you.